let's continue from our previous lectures on the stress state, and then the equilibrium equations, and then the equation for strain within a 3-dimensional continuum. And then later we have seen how to simplify the how to consider simplified stress states in 2-dimensional plane, so that we can speed up our analysis. And in today's class, let's continue a bit further and look at how we can describe the continuous variation of displacements within the continuum, then how we can relate them to strains, and then the stresses, and then how to develop our equilibrium equations for a continuum. So, let us go through a brief summary of the different stress states that we had seen in the earlier classes, then a bit more on the plane strain idealization, and then discretization of the continuum into smaller elements, then strain displacement and other relations, and then the derivation of the equilibrium equations, because that is the important step in our analysis. So, in the previous class we had seen these 3 2-dimensional approximations: plane stress, when all the stresses act within a single plane and all the outer plane stresses are 0. So, that happens in the case of a thin plate loaded in its own plane or a cantilever beam. Then we have a plane strain state where all the outer plane strains are 0. So, previously it was plane stress, all the outer plane stresses are 0. In this case it is plane strain where all the outer plane strains are 0, and this is a very common situation in geotechnical engineering, where we consider the analysis of very long retaining walls or embankments, tunnels, and so on. And the other case is the axisymmetric, where there is a symmetry, there is a radial symmetry around a central axis. See, this radial symmetry is there both in the geometry of the system and also the loading, and then the resulting stress states. So, if you have a radial symmetry like this, we can just consider a 2-dimensional stress state that we had discussed earlier, and then we will see a bit more in today's lecture. And this axisymmetric case is very common for circular footings under uniform pressure, or our own triaxial compression tests in geotechnical engineering, or the consolidation test, and so on. Okay. And in the previous class we had seen this example of a plane strain case, where we have a deep excavation supported by continuous sheet pile walls or diaphragm walls, and then in between we have the struts, which are compression members, which are placed at some vertical spacing and horizontal spacing. And how can we model this in a plane strain case? Because the sheet pile wall is not a problem, because it is a continuous member, but then these struts are discrete members, they are placed at some horizontal spacing and vertical spacing. And so, our thickness for plane strain case in the outer plane direction is 1, and if your horizontal spacing of the ties in a strutted excavation is SH, so actually these are the compression members, it should be just bar elements, is SH, and if the area of the each bar is A, then the area to be used in the plane strain model is A by SH. So, if the horizontal spacing of each of these struts in an excavation is SH, and if the area of each strut is A, then the area that we use in our plane strain analysis is A by SH. So, if SH is 0.5 meters, then we are going to consider twice the area, or if SH is 2 meters, then we will consider only half the area in our analysis. That is what we mean by prorating per unit length. And so now let us move on to the continuum, and what are the different steps. See, we are dealing with a displacement based approach, and we have seen the applications for discrete systems like the plane truss elements and then the plane frame and so on. And it is easy to imagine the number of nodes, number of elements, and then the number of degrees of freedom. But if you have a continuum, let us say you take a plate and let us say some dimensions, and how many elements are there. Depending on your imagination, you can consider very large number, and theoretically a continuum can have infinite degrees of freedom and infinite number of elements, but obviously we cannot consider all the infinite numbers. So, what we do is we draw some imaginary lines in the 2-dimensional case, or imaginary surfaces in 3 dimensions, to divide a continuum into finite number of elements, because we cannot really handle infinite number like infinite number of elements or number of nodes and so on. And to divide this continuum into a certain number of manageable number, we draw some lines in the 2-dimensional problems or surfaces in 3 dimensions, and we assume that elements are connected at discrete number of points located at the intersection of all these lines that we draw or the surfaces that we draw. And the interior of these lines or surfaces are treated as elements, and then we choose a set of functions to describe the variation of the displacements within each element, because once we define the nodal points, we know we are going to solve for them, but once we get the displacements at these nodal points, how do we find the displacements in the interior of an element? Because now we are dealing with a continuum, so that means wherever you see there is material, and so we need some methodology to determine the displacements in the interior of the elements. And now once you choose some function, so this function can define the state of strain within an element. Like once you have a function for the displacements, derivative of that will give you the strain. Okay? And so these strains will be in terms of nodal displacements. Then once you get the strains, we can get the stresses. Okay? And so what we do is then we develop our equilibrium equations as internal force is equal to external force if K is the stiffness matrix, K multiplied by a displacement vector U should be exactly equal to the applied force P. Okay? And in the process, we are going to satisfy this equilibrium only at certain number of degrees of freedom or number of points, not everywhere. So, the type of solution that we get, we call this as a weak form solution. It is not a the solution is not exactly valid at all the points, but approximately valid. Okay. So, if you have a 2-dimensional space like this, what we do is we draw some arbitrary lines, and these lines could be straight lines or curved lines or anything. It depends on the imagination of the user, and the intersection of all these lines is treated as a node, and the area in between these intersecting lines is treated as an element. So, here I have highlighted the nodes, and then also I highlighted the elements. So, this is a continuum, and theoretically it can have infinite number of elements or infinite number of nodes, but we have divided that into a certain number of nodes by drawing these lines, and the more lines that we draw, the more realistic your model will be. Okay. And so more closer your solution will be to the real solution. Okay. And these elements, they could be of different shape, like they can be quadrilateral elements or triangles or some distorted shaped elements like this. And so these triangles, they'll have minimum 3 nodes, whereas quadrilaterals they'll have 4 nodes and so on. Then if we have a 3-dimensional shape, we draw the surfaces. Let's say you consider a large cube like this. We have drawn 2 surfaces, one is yellow surface and then the other is a green surface, and then we divide this into 4 cubes, like 1, 2, 3, 4. Okay. And so then if you want, you can draw more number of surfaces and divide this continuum into smaller number of elements. Then once we get these elements, we can identify the nodes as the points at the intersection of all these lines or surfaces. An element is defined in terms of the number of nodes within the element, within the with number of nodes that are available, and typically we can have either 2D elements or 3D, and 2-dimensional elements we need minimum 3 nodes to define a 3-dimensional element like this, 3-node triangle or a 6-node triangle, and then 4-node quadrilaterals. And actually, depending on the shape that we have, we can decide the number of nodes. Then if we have more number of nodes along any line, we can either can even define a curved surface. So if you have a circle, that also can be approximated as equivalent triangles or rectangles, depending on the type of elements that you have in your program. Okay. And these are some of the typical 3-dimensional elements. We require minimum 4 nodes to define a 3D shape. Here is a 4-node tetrahedron and an 8-node brick element or a 20-node brick element, and so on. Let us say we have this x and y Cartesian coordinate system, and let us define one triangular element like this with the nodes 1, 2 and 3 defined like this, and we define these node numbers at the element level in the anti-clockwise direction. That I will explain a bit later. And at each of these points we have the displacements or the degrees of freedom, and in this case we have only displacements as the degrees of freedom. So at node 1 you have 2 degrees of freedom u1 v1, node 2 u2 v2, node 3 is u3 v3, totally 6 degrees of freedom, and AE is the vector of the displacements at the element nodes. Okay, so this is u1 v1, u2 v2, u3 v3, and these are the displacements at the nodal points. And let us say that at any point interior we have another displacement vector u and v, okay, which is function of x and y, and in general we can write u, interior displacement u, in terms of the displacements at the nodal points like this, n1 u1 plus n2 u2 plus n3 u3, or v is n1 v1 plus n2 v2 plus n3 v3. In here our n1, n2 and n3, these are called as the shape functions. Basically these are like our interpolation functions. Depending on the distance of the particular point from these 3 points, the value will change. Okay. And these shape functions, they will have a value varying from 0 to 1. Okay. And the internal displacement u is we can write it as some shape function matrix n multiplied by nodal displacement vector AE. Okay. That is u is n1 u1 plus n2 u2 plus n3 u3, and v is n1 v1 plus n2 v2 plus n3 v3. So, in terms of matrix and vector product, we can write like this. Our shape function matrix n is n1 0, n2 0, n3 0, and 0 n1, 0 n2, 0 n3, and this is our nodal displacement vector. And these n's are basically interpolation functions, but we call them as shape functions in the finite element context because they depend on the shape of the element, because they have one form for triangular elements and some other for rectangular elements, and then depending on the shape, like whether you have straight edges or curved edges, your shape functions might change. Okay. And the property of these shape functions at their own nodes, the shape function value is 1, and then at other nodes these are 0, and the sum total of all the shape functions is exactly equal to 1. These are similar to our influence functions that we come across in our structural analysis. So, if you have a moving load, the reaction at different supports is expressed in terms of some interpolation functions, and the similar things we can do for our shape functions. And we will define or we will derive what these shape functions are later on, because that is one of our major focus in any finite element analysis. Okay. So, let us look at the shape functions for a two-dimensional the two-node bar element, and let us consider a bar element having a length of L with node 1, node 2, and displacement at node 1 is u1, displacement at node 2 is u2, right. And we define or we develop the shape functions by different ways, and one is called as a generalized coordinate system, where we assume some polynomial, and the number of terms in the polynomial is equal to the number of nodes in the element, and then the polynomial order also we can decide based on the type of element that you have. And so, in this case, since you have two nodes, we can have two terms in the polynomial. U can be alpha naught plus alpha 1x. Actually, this is similar to our Rayleigh-Ridge procedure, where we assume the solution in terms of polynomial series, and the similar thing applies here. And this polynomial could be anything. It could be alpha naught plus alpha 1x, or say alpha 2x, or alpha 1x plus alpha 2x square, or anything, because since you have two nodes, you need to assume only two terms in this polynomial series, and we will discuss how we can or what is the basis on which we can assume these polynomials. So, so if you assume u as alpha naught plus alpha 1x at node 1, that is at x is equal to 0, u of x is alpha naught, and that is equal to u1. So, that means that our alpha naught is equal to u1, and at x is equal to L, u of x is alpha naught plus alpha 1 L, and that is equal to u2 at node 2. And so, our alpha 1 can be determined as alpha 2 minus u1 by L, and so our u of x, you can substitute the values of alpha naught and alpha 1 in this equation. U of x is u1 plus u2 minus u1 by L times x, and by grouping all the terms under the different displacements, we can write u of x is u1 times 1 minus x by L plus u2 times x by L, and we see that we have a linear variation that is corresponding to the linear polynomial that we had assumed. Okay. So, our n1 is 1 minus x by L, and our n2 is x by L, and at x is equal to 0, that is at node 1, your n1 is 1, and at x is equal to L, our n1 is 0, because if you substitute x of L, we get 0, and similarly n2 is x by L, and that is 0 at x is equal to 0, that is at node 1, and at node 2 our value is 1. So, our n1 plus n2 is exactly equal to 1, that is 1 minus x by L plus x by L, that is equal to 1. And if you want to determine the strain within the element, we just simply take the first derivative dou u by dou x, and that comes to just simply alpha 1, and alpha 1 is u2 minus u1 by L. Okay. And so, the determination of strains, we have already seen the definition of strains in the previous lecture, and if we use small strain definitions for plane stress and plane strain, our epsilon xx is dou u by dou x, and our epsilon yy is dou v by dou y, and gamma xy is dou u by dou y plus dou v by dou x. Okay. So, our epsilon, the strain vector is epsilon xx, epsilon yy, gamma xy, and actually we can write this as a product of an operator matrix like this: dou by dou x 0, 0, dou by dou y, dou by dou y, and dou by dou x multiplied by displacement vector u and v, where u and v are the displacements at the interior points. Okay. And this matrix we can write as L, that is the matrix of the linear operators, times u, and our u is actually n times AE. We have already expressed that in the previous step. Okay. Here we have seen that our internal displacement u can be written as n times AE, where n is the shape function matrix and AE is the vector of nodal displacements. So, our L times n we can written as B, and so our epsilon we can write as B times AE, where B is actually the shape the derivatives of the shape functions that we will see in the next step. So, epsilon is B times AE, and our B is actually, it is a very important matrix that relates the displacements to the strains, or the strains to the displacements. L is the matrix of linear operators, and B is the matrix of shape function derivatives, and B is L times n, and our U is n1 u1 plus n2 u2 plus n3 u3, and our epsilon xx you can write as dou u by dou x, that is dou n1 by dou x u1 plus dou n2 by dou x u2 plus dou n3 by dou x u3. And similarly, epsilon yy we can write as dou v by dou y, that is dou n1 by dou y v1 plus dou n1 by dou n2 by dou y u2 plus v2 plus dou n3 by dou y v3. Okay. So, this B matrix, that is the matrix of the shape function derivatives, we can write like this. So, the first row refers to epsilon xx, the second row refers to epsilon yy, these are the two normal strains, and then the third one refers to the shear strain gamma xy. So, dou n1 by dou x, dou n2 by dou x, dou n3 by dou x, and so on, and the second row epsilon y, dou n1 by dou y, dou n2 by dou y, dou n3 by dou y, and the third row is for the shear strains gamma xy. Okay. So, the number of rows in the B matrix is equal to the number of strain components. See, for the plane stress and plane strain, we have only 3 strain components. So, we have 3 rows. For axisymmetric, we have 4 strain components. So, we will have 4 rows, and for a full 3-dimensional case, we have 6 strains. So, we will have 6 rows in the B matrix. Then the number of columns is equal to the number of nodes in the element multiplied by number of degrees of freedom. So, for a 3-node triangle, we have totally 6 degrees of freedom, 3 nodes multiplied by 2, that is 6, and so we have 6 columns, 1, 2, 3, 4, 5, 6. Okay. So, once you have the stresses, the strains, we can determine the stresses as sigma is d times epsilon minus epsilon naught plus sigma naught, where epsilon naught are the initial strains and epsilon is the strain. Okay. And our displacement vector may also consist of initial displacements. Okay. And so, we get the total strain epsilon minus the epsilon naught corresponding to some initial strains multiplied by d plus initial stresses sigma naught, and the sigma naught in the geotechnical context could be the in situ pressures, and that depends on the geological conditions that we will see later. So, how do we write the B matrix for axisymmetric case? So, for the axisymmetric case, we have 4 strain components: epsilon RR, epsilon ZZ, gamma RZ, and epsilon theta. Epsilon theta is what we had seen in the previous class, circumferential strain, that is the change in the circumference because of any displacements, and this we have seen as u by r, and our epsilon theta is radial displacement u divided by the corresponding radial distance r, and that can be written as n1 by r u1 plus n2 by r u2 plus n3 by r u3. So, the first 3 rows for the axisymmetric case are similar to our B matrix for plane stress and plane strain, except in place of x we have r and in place of y we have z. Okay. And then the 4th row is our n1 by r, n2 by r and n3 by r, and since there are no v terms, we have zeros in these 2nd, 4th and 6th columns. And now, let us see how we can derive the equilibrium equation for a continuum, because this is what we require so that we can do all the computations, and we are going to follow the virtual work method. And we have seen this virtual work method earlier for the prismatic elements, that states that internal work done should be exactly equal to the external work done for equilibrium. Okay. And we will follow that approach, because that will give us an easy method for establishing the equilibrium equations. And let us say, let us define some quantities. When we have a continuum, we can have different types of loads. See, one is the concentrated nodal loads. Let us say that that is given by vector q, and with a superscript e that refers to the element, because we are going to derive all these at element level, and then we are going to assemble them into some global matrix corresponding to the entire structure. And AE is the vector of nodal displacements, and T is the traction forces on the surface. The traction force is nothing but the pressure. So, the external loading we can have as concentrated loads or uniform pressure or something like the traction force. And then the other type of force that you can have is the body force, vector of body forces per unit volume B, is basically because of the gravitational effect on the unit weight. Okay. So, gamma is our body force vector, and in general we can have a gamma in the x direction, gamma in the y direction, and so our B is the body force vector is bx and by, rho gx and rho gy, that is gamma x and gamma y. And if our x axis is in the horizontal direction and y axis is in the vertical direction, our gamma x could be just simply 0, because we do not have any gravitational force in the horizontal direction. And then in the vertical direction, since the weight is acting down, we will have minus gamma for gamma y. And the stresses in the element and sigma, and let us say epsilon is the total strain including the pre-existing strains, and sigma naught and epsilon naught are the pre-existing stresses and strains. So, our stress vector D we can calculate as D times epsilon, and epsilon is B times AE, okay, and we can expand the stress in terms of initial strain and initial stresses like this, D times epsilon minus epsilon naught plus sigma naught, right. Let us say we give some virtual displacement to the system that is already under equilibrium. So, under the action of all these, the body is in equilibrium, and we are giving some disturbance delta AE, right. At the element nodes, we are applying some virtual displacement field delta AE, okay, and because of that, the internal displacements delta U can be calculated as n times delta AE, right, where our n is the shape function matrix n1 0, n2 0, n3 0, 0 n1 0, n2 0, n3. The number of rows in the shape function matrix is equal to the number of degrees of freedom, then the number of columns is equal to the number of degrees of freedom in the element. Okay. So, the external work done, the work done by the concentrated forces is delta A transpose multiplied by QE, that is the work done by the virtual displacements, and then work done by the body forces is actually our body force is acting over the entire volume. So, it should be integrated over the volume, and delta U transpose B, where delta U is our internal displacements Ux and Uy transpose times B, that is Bx and By, and integrated over the entire volume, and our delta U is n times delta AE, right. So, if you take transpose of this whole thing, we get delta AE transpose and transpose B, and in here our delta AE refer to the nodal displacements, and they are not going to vary within the element. So, we can actually bring out this delta AE outside the integral, because these are constants for this element. So, delta AE transpose integral over volume n transpose B dV, where n is our shape function matrix n1 0 and 0 n2 0 and so on. B is our body force vector Bx and By, and similarly the work done by the traction forces, these are acting on the surface of the element. So, we need to take an integral over the surface of the element delta U transpose T, and once again delta U is n times delta AE. So, the transpose of that is delta AE transpose n transpose T ds, and once again delta AE is constant because they refer to the displacements of the nodes. So, we can bring this vector out delta AE transpose integral over the surface n transpose T ds, and and our internal work done is corresponding to the stresses and strains that we have inside, and our internal work done is delta epsilon transpose sigma, where sigma is our stress vector, delta epsilon is our strain vector, and our delta epsilon is B times delta AE, right, and our delta epsilon transpose, if we take a transpose of this delta AE transpose B transpose. So, actually whenever we take a transpose of a product, the terms get interchanged. So, that is what we see here, delta AE transpose B transpose, okay. And our sigma is D times B AE, this B times AE is our epsilon, right, minus D times epsilon naught plus sigma naught, okay. And so, our internal work done is integral delta AE transpose times B transpose, that is delta epsilon transpose dB AE dV minus integral of our work done due to the initial strains delta AE transpose B transpose D epsilon naught plus the work done due to the initial stresses delta AE transpose B transpose sigma naught dV. And by the virtual work principles, the work done by the external forces should be exactly equal to the internal work done, okay. So, equating these two, we get this inequality. This is the external work done that we have calculated earlier, and this is equal to the internal work done. And so, this delta AE transpose is common on both the left hand side and also on the right hand side. So, we can take them out, we can cancel them out on both the left hand side and the right hand side. So, we get B transpose dV, and once again our AE is the vector of nodal displacements, and this we can take out of the integral. We do not need to keep it in the integral. So, we have this bracket, large bracket, integral B transpose dB integrated over the volume multiplied by AE, that is equal to QE plus N transpose B dV plus N transpose T ds plus B transpose D epsilon naught minus integral of B transpose sigma naught dV, right. And on the right hand side, we recognize that it is a force vector. In fact, our QE is the vector of the applied forces, and the N transpose B is the vector of the force vector due to the body weight, and N transpose T is because of the surface pressures that we applied. B transpose D epsilon naught is the vector of nodal forces because of the initial strains, and B transpose sigma naught is the vector of forces because of the initial stresses. And so, actually here on the left hand side we have some quantity B transpose D dB integrated over volume and multiplied by displacement vector AE, and that is equal to force. So, this quantity, this unknown quantity B transpose dB must be stiffness, right, because as we recall the stiffness multiplied by displacement is equal to force. So, on the right hand side we have the force, on the left hand side we have something that we do not know what it is, B transpose dB integrated over volume V multiplied by displacement, okay. So, that means that this quantity in the square brackets must be stiffness matrix, B transpose dB dV. Okay, and actually it's easy to see the units for this, and let's see what they are. Let me write the pen. Okay. So our B is what? Is actually dou n by dou x and so on, and our shape function matrix is actually, it is dimensionless. So as we have seen, for the 2 node bar element, n1 is 1 minus x by L and n2 is x by L. Okay. So actually it has the units of 1 by L. Okay. So our B transpose, oops, sorry, we can see the units as 1 by L. D is the constitutive matrix. It has the units of stress, force by L square multiplied by 1 by L multiplied by volume L cube. Okay. So that has the units of force by L, that is the force per unit displacement. Okay. So we see that this quantity that we have here is it has the units of the stiffness 1 by L, and so this is the equation for the stiffness matrix of a continuum, and if we are able to evaluate this quantity, then we can get our stiffness matrix, and then we have this the vector of nodal displacements that we need to solve for. On the right hand side we have all these quantities. This is our QE is the vector of applied forces, N transpose B is the force vector due to the body weight, and N transpose T is because of the surface pressures, and this epsilon naught is the body force, the force vector due to the initial strains. And what is an initial strain in geotechnical engineering is very difficult to define, because our soil strata may have millions of years of history, and for defining the initial strains we need initial configurations that we do not know, and usually we neglect this and we do not consider initial strains, because we are more interested in knowing what happens after we construct a let us say building or an embankment or a tunnel, because we are more interested in what happens after you construct. Before you construct, the soil might have undergone lot of consolidation settlements or erosion or anything, but we are not really concerned what happened in the historical past, but what is going to happen after we construct. So in general, the epsilon naught is not considered in geotechnical engineering, so we do not usually evaluate this quantity, whereas for structural engineers it is a very important quantity, because the epsilon naught may be related to misfit of a member or because of some other reasons. And this sigma naught is actually, it's very important, it's the initial stress, and this could be because of our pre-existing stresses, and that is a very important one, and we can measure this quantity. So we can perform some pressure meter tests or the dilatometer tests, and then determine the in situ pressures. The vertical pressure is normally we estimate based on the unit weight, and then the lateral pressures we estimate by doing some field tests. Okay. And so the sigma naught is very important, and epsilon naught is normally we do not consider. Okay. And so if you are able to calculate all these terms, we will be able to do the computations for a continuum, because these things we have done for prismatic elements, for bar, beam and spring elements we have done this, and now we need to do the same thing for a continuum. If we are able to evaluate all these quantities, we should be able to solve our system of finite element equations for a continuum. Okay. So, I think this may be the last slide. Oh, sorry, I think yeah, have some more. Let me see. I think let me just. So, let us see. So, for the 3 node plane stress and plane strain elements, our B matrix is a 3 by 6 matrix. 3 number of rows corresponding to 3 strains and 6 columns corresponding to 6 degrees of freedom. And our B transpose is a 6 by 3 and D is 3 by 3. And our size of the stiffness matrix is B transpose DB, B transpose 6 by 3, D is a 3 by 3 and B is 3 by 6, and the total product is a 6 by 6 matrix. That is the stiffness matrix. This 6 corresponds to the number of degrees of freedom that we have in the element. And for the axisymmetric element, we have 4 strain components. So, B is 4 by 6, B transpose is 6 by 4. So, our D is 4 by 4. So, our size of the stiffness matrix is once again 6 by 6. So, for say for an 8 node quadrilateral, we will have 16 degrees of freedom. Our stiffness matrix will be a 16 by 16 matrix. Okay. So, the next step is we need to develop our shape functions. See, the shape function is the major component that we need to develop, because our shape function matrix is dependent on the shape functions, and then our B matrix is also dependent on the shape functions that we have n1, n2, n3 and so on. And what are different criteria for determining these shape functions? See, we have to ensure that as we are making the mesh finer and finer, we should be approaching the theoretical solution, the exact solution, and that we call as the monotonic convergence. As the mesh is made more and more finer by adding more number of nodal points, the solution should approach the exact solution, and that is called as the monotonic convergence. And some of the requirements are that the shape functions that we define, they should not permit straining of an element to occur when the nodal displacements are caused by rigid body displacement. Like for example, if I take this pen, if I apply some compression like this, there is some force, but let us say I take this pen and simply move it from one place to the other. That we call as the rigid body displacement, that all the nodes within the element are subjected to the same displacement. And if that is so, there should not be any forces developed in the rigid body in the body. And the shape functions should enable prediction of constant strain within the element if the nodal displacements correspond to constant strain. Say for example, if I compress this pen, there is some strain, and whatever may be the point within the pen, the strain is constant, because that is what is applied on the system, and our shape function should be able to predict this constant strain, and the strains at the interface between the elements need to be finite, and the continuity of displacements is ensured, and there should not be any singularity in the shape functions. So, once we define the shape functions at all the points within the element, they should have some finite value, they cannot have some infinite value, and that is what we mean by the shape functions not having any singularity. And so, one of the simplest methods is the generalized coordinate method that we can use for developing our shape functions. So, we assume a polynomial to express the internal displacements in terms of the nodal values, and the number of terms in the polynomial equation is equal to the number of nodes in the element. and the polynomial terms are constructed from the lowest order, and as we go further we add higher order terms, like first constant term, next linear term, and then the quadratic term, cubic term, and so on. Okay? And the polynomial should be spatially isotropic, so that the finite element derived can be applied directly to any coordinate system. So, our coordinate system is also dependent on the user. So, some users may prefer this coordinate system, like x is along the horizontal axis, y is along the vertical axis, or you might even interchange. Somebody might want y to be horizontal, x to be vertical, or say we might have we might flip, so that our y is positive downwards instead of positive upwards, and x is horizontal. So, whatever may be the coordinate system that we have, our result should be the same. So, if you get 10 millimeter displacement here, we should get the same 10 millimeters even with other coordinate system. So, actually in this the value might change to minus 10, and here it could be plus 10, because our y direction displacements are changing. Okay. Other than that, the values themselves should not change, and that is what we mean by spatially isotropic coordinate system. Whatever may be the coordinate system that we have, we should get the same value. And to help us in choosing the terms, we have a Pascal triangle, and this particular one is in 2 dimensions in terms of x and y, and we need to include a constant term in the polynomial, and then the linear terms, and then quadratic terms x square, x y, y square, and then the cubic terms x cube, x square y, x y square, y cube, and so on, the quartic terms, quintic, septic, and so on. Okay. So, this and there is one example given here. Previously we had derived the shape functions for a 2-node bar element, and let us consider a 3-node bar element with node 1 at x is equal to 0, node 2 at x is equal to L, and node 3 at mid length L by 2. And because we have 3 nodes, we need 3 terms, and so our displacement function u of x can be assumed as alpha naught plus alpha 1 x plus alpha 2 x square. Okay, we can have up to the quadratic term x square. So, if you substitute x is equal to 0, u of x is alpha naught, and that should be equal to u1. Okay. And similarly, we can set x is equal to L when your u is u2, and x is equal to L by 2, u is u by 3, and so on. Okay. And so, by solving, we can get the 3 constants alpha 1, alpha naught, alpha 1, and alpha 2, and then substituting and then grouping the terms under u1, u2, and u3, we get like this. Our n1 is 1 minus 3x by L plus 2x square by L square, n2 is 2x square by L square minus x by L, n3 is 4x by L minus 4x square by L square. And if you add up all the shape functions n1 plus n2 plus n3, that should come as 1, and that is indeed 1. Like if you add up all the terms, you get 1, and then our strain dou u by dou x is epsilon x, that is if you differentiate u1 times minus 3 by L plus 4x by L square plus u2 times minus 1 by L plus 4x by L square plus u3 times 4 by L minus 8x by L square, right. And if you apply a rigid body displacement for the system, let us calculate strain in this system, and rigid body displacement is when u1 is equal to u2 and u3 is equal to u3, and let us say that is equal to u bar. And so if you calculate epsilon xx, and because u1, u2, u3 are constant at u bar, we can take it out, and then if you see the sum total of all these bracketed terms is equal to 0. So that means that our strain is 0 within the element if we subject the body to some rigid body displacements. Okay, that is what we require as one of the conditions for monotonic convergence. And similarly, we can examine whether we can predict a constant strain state within the element. Let us say our u1 is 0, that is the left side node is fixed, and the right side node is deformed by u, and the central node should deform by u by 2, right. So our epsilon xx is 0 plus u times 4x by L square minus 1 by L plus u by 2 times 4 by L minus 8x by L square. These are the terms that we derived earlier. So our epsilon xx is, if you take the total of this, it is just simply u by L, and that is constant in the element. It is not a function of x. So that means that if your applied displacements are corresponding to a constant strain state, we should be able to predict a constant strain within the element. Okay, that is u by L. Okay. And so the shape functions that we derived, they correspond to monotonically convergent solution. So we can say that our polynomial that we assumed is will ensure our convergence. Okay. So if you assume a polynomial like this, alpha 1x plus alpha 2x square plus alpha 3x cube, or alpha naught plus alpha 2x square plus alpha 3x cube, it is possible, these are also admissible, but then we may not be able to satisfy our monotonic convergence requirements, and because of that our solution may not be accurate. So that we are going to see more in the next lectures. So just to summarize, we have seen how to divide a continuum into some finite number of elements, and we have seen continuous variation of the displacements within the element by developing our shape functions, and the shape function matrix n for interpolation of displacements, and the strains from displacements in terms of epsilon is b times u or b times a. Okay. And our we have seen the equilibrium equations for a continuum. Okay. So this we will do a bit more in the next lecture, so that we understand how we can do the analysis. Okay. So thank you very much.